Hi, everyone, and welcome back. So, we're still busy with our first day of the Open Science Room program here at the OHBM, and we're still excited to welcome everyone from our global community via the OHBM platform and also via Crowdcast and our other streaming platforms. And today we'll be speaking about demonstrations in this session. So, we'll have a bunch of demonstrations. If you want to get more information about this, you can have a look at the links that we provide on this slide. The first one being our OSR website, and you can find more information about the speakers and their specific talks there. You can also share whatever you find interesting on Twitter. So we have our Twitter username there and Twitter hashtags OHBM 2020 and OSR. So please feel free to share. And you can also join the discussion now and afterwards about the OSR in general, but also about this theme and these demonstrations in particular on the Mattermost channels that we provide there.
So in this session of demonstrations, people will be showing us some software that they've developed to address issues around the next generation of data sharing and open data. So we'll have 4 talks of 7 minutes each, followed by 20 minutes of Q&A where all speakers will be together to answer your questions. Some speakers will be available in this time zone that you're watching from, but potentially not all of them. If you have questions for speakers who aren't going to be available in this time zone, we'll endeavour to get those questions over to them.
So we'll be using Crowdcast as the main platform for Q&A for all of us and for our global participants. We asked you to use that text chat function to ask questions and upvote them. But if you aren't able to use Crowdcast, you can also post your questions via the chat function in the OHBM virtual conferencing platform or otherwise through Mattermost. We are very keen to get your feedback. So we will add some polls during this session and ask you for feedback on the OSR itself, but also feedback that we can give to the speakers. And then finally, we ask everyone joining here today to treat each other with respect and kindness. We all agreed to abide by the code of conduct when we registered for this event. And we ask you to, if you experience or see a violation of this code of conduct, to report it according to the process that's outlined in the code of conduct on the OHBM website.
So now it's my pleasure to welcome our speakers. First, we'll be hearing from Nikita Belli, describing the BidsMem flexible bidsifier for multimodal datasets, followed by Ana Luisa Pino, speaking about individual brain charting dataset extension with their 2nd and 3rd data release. After this, we'll hear from Paolo Di Maio with the open and shared representation for neuroscience, followed by Doreen Heiser discussing sharing MRI datasets while protecting the participants' privacy and 2 ways you can get started with this. So now I'll hand over to the speakers. Thank you so much for joining us again today, and we look forward to hearing from you in the Q&A.
Hi everyone, I'm Nikita Belli from Liège University in Belgium, and I'm here to present a small tool called BidsMem, which bidifies multimodal datasets. Actually, it supports MRI, PET, and EEG, but it can be very easily extendable to other data formats and modalities. To demonstrate it, I start with some random data set composed of one series with structural MRI data. And as you can see, it's just flat collection of the DECOM file. In order to bidify it, I need to put it in specified form, which is made by command BidsMe prepare for preparing the data, and then I put the input directory and output directory. After it runs, in the prepared data set, the original data is structured following BIDS-like structure. So it has the subject folder, session folder, then folder with for this modality. In this case, it's MRI, and DICOM files with anatomic structured in the series folder. So once the data set is prepared, and as BIDS doesn't accept DICOM as file format, they must be converted by any exterior tools. I use DSM to NICs, but anything will go at condition it doesn't create JSON files and doesn't rename the files except the extension. And I also need to remove all converted DICOM files, so program will not double count it. Once these files converted, I need a configuration file which will tell exactly how to Bidsify this data set, and I already prepared it to save time. This configuration file is written in YAML language, and it follows the hierarchical structure. At the top level, you have the modality. Just below the modality, you have file structure. In this case, it's BidsMe NIFT, which means it's a NIFT file with a DICOM header dumped in the JSON file. And you have a dictionary with BIDS modalities, which are the same as the BIDS folders, subfolders in Bidsify dataset. And inside each modality, you have a list of different cases, which all identified by what is written in the attribute section. So for this case, it's asked for protocol. It's a check if protocol name is ANAT T1 weighted. And for this case, it checks if it's a T2 weighted. And if particular file checks this case, then this file is bidsified accordingly what it's put in the bid section and in the suffix field. In the bid section, you can put either the text like here, so it will be bidified with the corresponding text, or if you enclose it in the single brackets, it will search in the header corresponding value and replace dynamically for each new file. Also, in the JSON section, you can specify which data will go to the sidecar JSON file. Again, you can put either just a plain text, or you can retrieve some data dynamically. So once this file is ready, you just run bidsify command, and you have your dataset actually bidsified. As shown here, it has standard bid structure, including the participant.tsv file and JSON file, folder for subjects. In this case, we don't have a session, so there are no session folder, but you have both scans.tsv and JSON file containing the acquisition time for each file. And in the modality file folder, you have both NI files and corresponding JSON file. And in the JSON file, you have fields which are entered manually in the configuration file, and you have some fields which are filled automatically during the bidification. Actually, these files are converted from NIFT to DICOM, so there are a lot of fields missed. In normal DICOM case, you will have a lot of technical information which is filled automatically. So in total, you have your fully bidified dataset. This tool is available on GitLab and GitHub. GitLab, it's private university server, but it's accessible from exterior. And GitHub, it just mirrors this repository. It also contains an example dataset with several configurations, variants, and plugins with which you can play. And I think I'm on. So thank you for your attention, and that's all.
Hello, thank you very much for the opportunity to present the latest updates of the individual brain charting project here in the Open Science Room event. So in this project, we are developing an open access neuroimaging dataset dedicated to map cognition in human brain. And we just made publicly available the second and third releases that I will next talk about. So in brief, in the IBC dataset, we acquire higher spatial resolution fMRI data, concretely at 1.5 millimeters. And it refers foremost to task fMRI data with a strong emphasis in a task-wise dimension, meaning that we collect data from many tasks, most of them reproduced from previous studies, in a fixed cohort of 12 adults and fixed environment. Also, the IBC project, it doesn't stand for a longitudinal study, meaning that we don't systematically undertake repeated measurements of the tasks. So the tasks of the second and third release already bring together a wide variety of new psychological domains. Concretely, in a second release, we have mental time travel battery, in which we access mental time and space shifts in two possible cardinal directions. We have a preference battery, in which we access positive incentive value. We have a battery of the theory of mind and the pain matrices. We have also two tasks on numerosity that are accessed through two different experimental paradigms, one in visual short-term memory and another one on enumeration. We have also a task accessing the self-reference effect, and also a task on attentional control, in which we measure synchronized responses while watching a short movie of Alfred Hitchcock. And in a third release, totally dedicated to the visual system, we have three tasks. One, the clips tasks on passive watching of naturalistic scenes. Also, we have a classic retinotopy task, and a task on movie watching of the Riders of the Lost Arch. And these two releases bring 60 more elementary contrasts, and together with the first release, we then have a total of 120 elementary contrasts. So the behavioral protocols of the tasks have been either developed or reproduced in close collaboration to many research centers all around the world. But we are still looking for new protocols. So if you want to collaborate, please contact and share your protocols with us. In terms of software tools, we rely in these two releases on open source frameworks, namely in Experiment, PsychoPy, and PsycToolbox. We have also started to do some quality data checking in order to assess that the neuroimaging data truly reflect a response to behavior. And concretely, in a second release, we tested whether similarity between activation maps of elementary contrasts fits similarity between their cognitive description based on extraction of terms from the cognitive atlas. And we did this by computing correlation matrices in two different ways. So on the left side, we compared the average activity at every voxel evoked by each condition, whereas on the right side, we compared the occurrences of mental concepts in these conditions. And we can clearly see that they share both some level of similarity, which is quantitatively confirmed by the Spearman correlation coefficient. But what is interesting to note here is that if we add the first release, this similarity gets higher, meaning that as many more tasks we had to the data set, similarity between activation maps and that in their cognitive description also gets higher. So regarding the third release, we employ data-driven methods in naturalistic stimuli related data. Concretely, we show here results from the analysis conducted by my colleague Sweta Shankar, in which she performed the fast shared response model decomposition of the rider tasks into 20 components. And here we display the first 3 components. So in terms of accessibility, the IBC data is organized according to BIDS specification. Documentation can be accessed on the YBC website. So you can go to the data tab and then you can click here and access to the documentation. Also, the raw data is available in the Open Neuro Repository Collection 2685 and in eBrain's platform of the Human Brain Project. And then the data derivatives are available in NeuroVault, concretely the unthresholded Z maps of the all contrasts. So we can take as an example the enumeration task that I talked about. And then we can see the activation in orange red of the enumeration of the main effect of enumeration versus fixation, and then in blue the reverse contrast. And here we see the corresponding metadata of the image. Also, we have 2 dedicated repositories on GitHub for the behavioral protocols and the analysis pipeline of the dataset. And I'd like to thank the Human Brain Project for the funding of this research, to the all IBC volunteers and collaborators from INRIE and Neurospin in Paris, particularly to all my colleagues from Parietal team and to my supervisor Bertrand Thirion for the all support. And you can chat with me at the OHBM poster session. And thank you very much for your attention.
Thank you for accepting my talk, Open and Shared Representation for Neuroscience. So the background is I come from complexity science, information theory, and knowledge integration, a bit of a mix. The motivation for doing this work is because neuroscience is the ultimate frontier and is relevant to many other fields. To facilitate learning, education, to enable the evaluation of research claims. Please note that this is not a demo, and it's a very fast, at speed of light overview to make the point about open and shared representations. I got to this topic because I was looking at how neural networks and machine learning are actually modeled on brain function. But I found no tangible commonality between the brain data or neuroscience and neural networks. Really, I couldn't put my finger on it. So what knowledge from biological networks neural networks can help to research, model, and develop artificial neural networks. In particular, we then look at defined examples such as spikes. And this is not easy to answer. Despite decades of research and a lot of data available, the answer is not straightforward because many reasons, and one of these reasons is the fragmentation. Why open and shared? I'm sure everybody knows the benefits because it's explicit, explainable, trustworthy. It can be better understandable, verifiable, reproducible, less resource intensive. Once it's open and shared, one has to spend less time working it out. It's interoperable and more interdisciplinary. So at the moment, the main issue that I've come across is that to learn from neuroscience for the purpose of developing AI, neuromorphic systems, etc., we need to understand brain data. The brain is the most complex and advanced information processing entity that we know of. So the problem is the lack of alignment and mapping between the different data sets. I'm referring to internal alignment within neuroscience branches. So neuroscience itself is very diverse. And external between neuroscience and, say, artificial intelligence or systems engineering. These are usual misalignment issues. There are different vocabularies, concepts, structures, and they're common in other fields. In neuroscience, I found a few different standards in use for representing brain data, and one of them is NeuroMel. BidsMem is becoming very popular, and Neurodata Without Borders, they have their own schemas. And some of these standards may overlap and some may differ. So the problems with this fragmentation is that each schema offers a different views. They're not interoperable. They are generally strongly coupled with software environments. So you need Python to read the data set. Current standards mostly reflect data file formats. So when you look at the schemas, they are just a dump of the file format in use by that particular system or software. So they haven't been developed following proper knowledge modeling. They're also viewable via compilers and not available as visual documents or schemas. So there is limited usability. You may have heard of knowledge representation. It's generally symbolic, non-symbolic, neurosymbolic. I underline symbolic because it's the one which symbolic knowledge representation, I think, is the one which is going to be most useful. Also neurosymbolic, which is kind of between the two. And knowledge representation, you have to check it out if you're not familiar with it. There is a lot of literature, but basically it's about identifying entities, structure, models, relations, and generally making explicit the system logic. So there are a variety of approaches that can be followed to devising open and shared data. And for example, computational, theoretical, simulation, cognitive, systemic, which is more integrated or applied. And I tend to adopt a combination. So when we start thinking of integrating different methods to make the brain data explicit and shared, we have to look at all the neighboring disciplines. We can learn from other domains. So as a starting point, we use knowledge representation from AI, which is a well-defined, well-understood field. But then we also need to combine approaches from systems biology, transomics, and bioinformatics. There is a lot of very relevant work that can be useful. So very quickly, I'm going to pull up a few images from related work. Mostly looking at functional connectivity research because it's the most dynamic aspect of neuroscience that looks at cognitive and behavioral aspects. So in the following few slides, you'll see some slides with the links of where they come from, and I will show why I think they're relevant to devising open and shared representations. So this example from Nature is multi-level. It shows how your data can have different levels, neural, observational, and inferential, for example. This one shows different data models, kind of representation models, rather. Prototype learning, information integration, arbitrary categorization, and rule-based categorization. These are different ways that data can be combined. Here we can see different levels of abstraction that need to be addressed in an open and shared representation. So whenever you devise your data set, you can explain where it belongs at network, connectivity, activity level, for example. All of these levels contribute to make the neural process. This slide shows how ultimately, although the data generally comes from specific studies which look at individual problem spaces, so to speak, like neuromarkers or connectivity matrix, when we're opening and sharing our data, we need to show it in relation to a whole system approach. And I found useful the reference to information geometry. For example, when we are devising our whole system data, we can take into account different configurations for the information from WYSUMI. So my area of work is to facilitate transformation between data sets and schemas, to enable natural language querying of brain data, and in particular to make neuroscience research data available and relevant to other disciplines and fields of application, including social sciences. So brain data is going to be very useful to a lot of other research. However, at the moment, it's very difficult to use. The work to be done, I see that neuroscientists and programmers are doing great work. There is a lot of research data, there are a lot of software tools and applications. However, not enough ontologists, analysts, systemists are in the mix. High-level meta-analysis viewing brain data is not yet there. Very tentative roadmap. I am working on identifying and mapping these different standards, and scoping a specific subset of data sets that I can work with, select methods, apply methods to the corpus, evaluate, and iterate. This is my current roadmap for my current research. So thank you very much, and thank you also and especially to the people who are doing great work in this space. Some example of projects like NDA, there is software and data out there. So there is a lot of data produced and published every day, but there's a lot of there are barriers. It's still very, requires a lot of study to understand and make use of them. I think shared and explicit knowledge representation of this data can help advance the state of the art across sciences. Thank you.
Hi, my name is Doreen. I'm currently a data manager at Erasmus University in Rotterdam and Leiden University in the Netherlands. I work in a developmental neuroscience group where a lot of sensitive MRI data are collected. And that is how I got involved in the initiatives that I will talk about today. If you have any questions, please feel free to ask them after this demo, email me, or follow me on Twitter. So in this age of the corona outbreak, the importance of sharing research data has become extremely clear, and it's getting a lot of attention. So this, as it could potentially save lives in this age now. So this may help in making sharing data the gold standard, which we open science enthusiasts can only agree with, of course. But when sharing data in the EU, we do need to take into account privacy law, especially specifically the GDPR, the General Data Protection Regulation, which was introduced in 2018. The aim of this regulation is to protect the privacy of EU citizens as much as possible and to prevent misuse of personal data. So under this regulation, there are two terms to be familiar with: anonymous data and personal data. Anonymous data is not in any way traceable to individuals. So re-identification should also not be possible. So if you have a file that includes the conversion from participant number to participant name, the data are officially not anonymous. But truly anonymous data can be shared without any restrictions. And then on the other hand, we have personal data, which is data that is traceable to an individual. And often it's relatively easy to identify directly traceable information, such as names or pictures. But it gets more difficult when determining whether information is indirectly traceable or not. So data can be indirectly traceable when there are cases of which there are only a few in existence. For example, a very old man in a certain neighborhood of London. But data is also indirectly traceable when you can identify someone by combining data with publicly available data, or when re-identification is still possible. And that is the case in case of pseudonymous data. So that often looks anonymous, but it really isn't. Pseudonymous data are still considered personal data. And so if you want to process or share personal data, you need a legal ground or lawful basis. And in research, this is often informed consent by the participant of the research. So for brain MRI data specifically, mainly high-resolution anatomical images contain many details, such as the face, but also every brain is unique, so it could potentially function as a fingerprint. And also, if we share such data openly, even if the face has been removed from the scan, there's a possibility of matching brains and identifying someone in that way. So there is some discussion about this issue, but in our opinion, brain MRI data should be considered pseudonymous data at best, and therefore we need to take the necessary precautions as to the legal grounds and way of sharing. So the fact that the privacy of EU citizens is well protected doesn't mean that we should give up sharing neuroimaging data. Sharing research data is still something that's desirable for example, reproducing results, combining samples, or letting others perform analysis on the data. And for the past year, there have, of course, been many initiatives, and I will talk about two of them. The first is a small-scale initiative that I have been running to create a decision tree for researchers in the Netherlands. And the second is a larger initiative, which has been going on for a few years already, which is called the Open Brain Consent. So during several encounters with researchers, we noticed that there is a lack of awareness of the GDPR regulations amongst researchers, or at least about the application of it for neuroimaging data. And in our department, there was also almost no one with any experience in sharing neuroimaging data, and people found it difficult to find the right information in university contexts. So that is why we decided to create a relatively simple decision tree that can help increase awareness of the GDPR regulations for neuroimaging data and give researchers some directions as to where to start and what to think about. So the current decision tree is targeted at researchers at Dutch institutes who collect and wish to share brain MRI data, and it will soon be published on Zenodo. So here you can see a first version of the decision tree. The tree asks, among others, which type of data you want to share and whether you have taken the necessary precautions to do so. The orange boxes give some options for MRI data sharing, but those are really focused on the Netherlands. So in the future, we may develop a decision tree for a wider audience, for example, for researchers in the entire EU, and adjust these options. So if you have any ideas about this, feel free to let me know. Then moving on to the Open Brain Consent. Open Brain Consent was initiated a few years ago to create unity in the informed consent forms on neuroimaging studies, allowing the sharing of those data. And from last year's OHBM onwards, Stefan, Pierre, and Cyril have been working on addressing the GDPR aspects specifically. So the OBC is a much broader audience comprising of all researchers aiming to share neuroimaging data inside and outside of the EU. And the website already contained an ultimate consent form, which can be used outside of the EU, but there now is also a GDPR edition of the ultimate consent form, and a data user agreement template with translations in 11 languages, if I'm correct. So here's an example of the first version of the ultimate GDPR version. It creates paragraphs about, it contains paragraphs about usage and storage of the personal data, who has access to which type of personal data, how long it will be stored, withdrawing consent, and finally sharing the data with researchers outside of the EU by means of a data user agreement. And I've pasted the link here on the slide if you want to go and see it. So the data user agreement needs to be signed by the person with whom you share the neuroimaging data. And it states that the user will comply with all relevant rules and won't try to identify the individual participants. And also the person cannot share the data with third parties and should reference the source of the data when publishing about it. So in the future, the OBC working group will be working on a GDPR-specific frequently asked questions page. And there will also soon be a pre-printed article about these GDPR-related templates. Yeah, okay. So that was my story for now. If you have any questions about the decision tree, feel free to email me or follow me on Twitter and message me there. If you have any questions about the OBC, the Open Break Consent Initiative, you can contact Stefan Heunis. I've also pasted his email address and Twitter handle here. So thank you for listening, and hope to see you soon.